over here, I have two sets of points for which I want to try and find a polynomial whose graph goes through these points. So the reason that you might want to do this is if you're in a field where you have a set of independent and dependent variables and you want to try and find a polynomial whose graph goes through those points and predicts any other points that you might want to input into this model, then this might be a good idea to try. So the process of trying to find a polynomial whose graph goes through some points is called polynomial curve fitting. And essentially, we take a given set of points and we try and find a polynomial of some degree that goes through all those points in this process. So go ahead, pause this video and see if you can try and figure it out on your own of like how you might try and find a polynomial like this. And if you arrive at an answer, come back to this video to check it. Otherwise, you can just watch me solve it. So go ahead, pause the video, give it a shot, and once you're ready, come back.
Before getting into the video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I go into these concepts more in depth and have problems and solutions attached to every single video. The guide itself is free, however the videos do take a bit longer to make since they're a lot longer than these videos, so go ahead and check the description to see if I've released the corresponding Ultimate Linear Algebra Guide video for this one yet, and if I have, go over there. Otherwise, you're welcome to keep watching this video until I do eventually release the guide. Also, make sure you subscribe to my channel so you'll be notified when I release the Ultimate Linear Algebra Guide video for this concept. Okay, let's get back into the video.
Okay, so the first thing that we need to do is decide the degree of the polynomial that we're going to try and use. So here, we always use a polynomial of a degree that's one less than the number of points we have. For example, here we have 3 points. So we would want to try and use a polynomial of degree 2. So let's go ahead and do that. So here, since we have a polynomial of degree 2, we want to write out the general form of a second degree polynomial to see what our final polynomial might look like. So we might have, or we will have a polynomial that will look like this. We'll have some constant term plus some first degree term with the coefficient of a1 plus some second degree term with the coefficient of a2. So this is what our final polynomial will look like, and this is the polynomial we have to try and take these points and fit them to. So we have to have the same number of equations as the number of points we have, and to do that, we use each point to create an equation. So the first point that we have right here has an x value of 1. So we would use the point here with a function of p of 1, since x is equal to 1. And we would take this and substitute it in for every x position in this function. So our constant term would remain the same because it's not associated with any x. Here we would just have a1 because a1 times x is just a1. And here we would also just have a2 because a2 times 1 squared is just a2. And this is going to be equal to the y value because that's the value associated with the function at x equals 1. So this is going to equal 4. Now we're going to do the same thing for the next 2 points. So here we would have p of 2. And we would substitute in x equal to 2 for every single place within our function. Since a0 is a constant term, once again, it would remain the same. Instead of a1 here, we'd have 2a1 because a1 times 2 is 2a1. And here we would have 4a2 because we would substitute in x as 2, and 2 squared is 4, so we'd have 4a2. And this would equal 0 because that's the term associated with our function at x equal to 2. Finally, for the third equation, where we have a value of x equal to 3, as seen in this point right here, we would have our constant term remaining the same, plus 3a1 because x equal to 3 and a1 times 3 is 3a1, plus 9a2 because a2 times 3 squared is 9a2, and x equal to 3. And this would equal to 12 because that's the term associated with the function at x equal to 3. Cool. So now we have a system of equations that we can use to solve for a0, a1, and a2. So if you weren't able to arrive at a polynomial on your own earlier, you should be able to now. So pause the video, go ahead, solve the system like we've done in so many previous videos. Come back here and check your answer. Okay, so hopefully you gave that a shot. If you're having a little bit of trouble with solving a system of equations, I recommend you go back and watch my videos on Gaussian elimination and Gauss-Jordan elimination because I go much more in depth on how you might solve a system like this. But here I'm just going to go ahead and speed through it because I expect that you're already fluent with it and I'm going to use a calculator. Okay, so let's go ahead and write out the matrix associated with this system. So the first column would contain a 0. It has coefficients of only 1. Our second column would contain the coefficients of a1, which are 1, 2, and 3 from this system right here. And the last column of our coefficient matrix would contain the coefficients of a2, so 1, 4, and 9. Now we go ahead and add on or augment a column with the constant terms associated with all of our equations, or 4, 0, and 12. We can go ahead, row reduce this matrix. I'm going to go ahead and use a calculator to do this, but you could probably do this by hand. In fact, you definitely could do this by hand, but I'm just going to use a calculator for the sake of time. And once we row reduce this matrix, we get the following. The first row would be 1, 0, 0 with a 0 equaling 24. The second row would be 0, 1, 0, with a 2 being equal to negative 28. So I'm just going to write that down. And the last row would contain 0, 0, 1, and a 2 would equal 8. So a0 is equal to 24, a1 is equal to negative 28, and a2 is equal to 8. So let me just write that down. a0 is equal to 24, a1 is equal to negative 28, and a2 is equal to 8. Now that we have the values of all of the coefficients of our terms, we can take these and substitute them back into our general form to arrive at our final polynomial. So here we would get that p of x is equal to a0, or the constant term, which we found that to be 24, plus a1 times x, which we know is negative 28 times x. So instead of plus the term, it would be minus 28x, plus a 2x squared, which is going to be 8x squared. So this is the general polynomial that we'll arrive at after going through this process. Now let's go ahead and do the same thing for this question right here. So pause the video and try and solve this question on your own and come back to it when you think you've arrived at a solution. Okay, so if you tried solving this problem on your own, you probably realized that the numbers are nowhere near as friendly as the last question, because we have terms that are like 2,000 greater than those in the last question. So what we have to do here is apply a transformation that will make the terms a lot easier to work with. You don't have to do this, especially considering you have a calculator, but when you end up making your matrix and it looks a lot more ugly than the previous matrix we've been working with, it's a lot nicer if you have better terms that are more manageable. So let's go ahead and apply a transformation so that you have another tool that you can use when solving problems. So the transformation that I'm going to apply here is that we can say that z, or any variable we come up with, I'm just saying z here because x, y, z, but it's completely up to you, is equal to 2000, or rather, sorry, x minus 2000. Now, the reason I'm doing this is because I see that every single term here is about something greater than 2000. So if we had 1, 2, 3 here, it'd be a lot easier to work with than 2001, 2002, 2003. I essentially just reduced the terms to something easier to work with. This isn't the only transformation you can apply. Another probably easier one that you could apply is that z is equal to x minus 2001. However, you're going to see the reason I applied 2000, but it's not the only transformation you could apply, and other transformations would work just as well, if not better. So if we say that z is equal to x minus 2000, we need to go ahead and rewrite all of these coordinates in terms of z instead of x. So since we're only applying this transformation to x, the y coordinate will remain the same, and we only really wanted to apply transformation to x because that's the only term which is not that easy to deal with. y seems pretty easy to deal with. It's just 4, 0, and 12. There doesn't seem anything that ugly there. But x is huge. So let's go ahead and do that. Here, instead of x, we have to write z. So since z is equal to x minus 2000, we'll get 2001 minus 2000, which is 1. So our first point will become 1, comma 4. Once again, y remains the same. This is no longer x, but this is z. The second point would be 2002 minus 2000, or 2, comma 0. Once again, this is z, not x. And lastly, our third point would become 2003 minus 2000, which is 3, comma 12. Our y remains the same, and this is z. So we have 3 points that are a lot easier to deal with than when we had 2001, 2002, and 2003. So we can go ahead and use these points to create a system of equations that we can solve in order to find what our values for A0, A1, and A2 are. So now this is the point where we can go ahead and apply the exact same process for the other problems since we've transformed all these points. Let's go ahead and find out which degree polynomial we have to use. So the degree polynomial is always 1 less than the number of points we have. So since we have 3 points here, we would use a second degree polynomial. So let's write out the general form of a second degree polynomial so we know what our final answer will look like. So since this is the same as the last question, it will just look like this. A0 plus A1x plus A2x squared, where A0, A1, and A2 are what we need to solve for. And we can create a system of equations. If you haven't noticed this already, these points are the exact same points that we dealt with earlier. That's why I applied this specific transformation that z is equal to x minus 2000. If this was a homework or a test, I would recommend you, in fact, apply the transformation that z is equal to x minus 2001, because that would create a zero term, which is easier to deal with because both of these would equal 0. But here I use this since we've already dealt with these points and we already know what they're equal to, so it'll save time. Since we know what these points are already equal to, we can go ahead and use this in our system. But before we do that, here, since we're no longer dealing with x, we're dealing with z, we need to rewrite our polynomial function. So instead of p of x, we're going to have p of z, because that's now our independent variable with these points right here, is equal to a0 plus a1z plus a2z squared. So now we can go ahead and solve for a0, a1, and a2 using a system that we already had. You're welcome to pause the video and come up with the system yourself and solve the system, but since this is the exact same system that we used in the last problem, I'm just going to go ahead and write out the solutions. You'll get that a0 is equal to 24, a1 is equal to negative 28, and a2 is equal to 8. These are the exact same solutions we got last time, which makes sense because it's the exact same system. So we can go ahead, plug this into our general form. Remember, we're using this general form, not this one over here, because this is the general form with z in it. This was the general form with x in it, but since our independent variable is now z, we have to use just this general form right here. We're going to get p of z, which is our new independent variable, is equal to our constant term, plus, well, it's not going to be plus, it's going to be minus because this is a negative here, minus 28z, and it's going to be plus 8z squared. So if the question was asking for a polynomial in terms of z, we could leave it here, but we want a polynomial in terms of x, so we need to take this equation right here and substitute it back in here, so we get an equation in terms of x. So since we know that z is equal to x minus 2000, we can get a polynomial in terms of x to equal, well, 24 is just going to remain as 24, minus 28 times z, but we want it to be in terms of x, so z is equal to x minus 2000, plus 8 times z squared, so x minus 2000 squared, because that's what z is equal to. So to summarize here, essentially the first thing we did was apply a transformation to all the x terms here to make the points easier to deal with. We said that z is equal to x minus 2000. When we got the easier points, we ended up in creating a polynomial in terms of z, not x, because that was our new independent variable. Once we did that, we went ahead and substituted in the thing that we had for z here, that z is equal to x minus 2000, and we ended up getting a function in terms of x. You could simplify this further, and you'll get a function that's completely in this form, where instead of us having x minus 2000 in terms of the x here, we would have everything perfectly in terms of x in this general quadratic form, but I'm not going to do that because that's going to take a while and it's more of a test of your algebra than your linear algebra, and I'm confident you guys will probably be able to do that on your own.
So that's the end of the video. If you have any questions or spotted any errors, you're welcome to leave them in the comments, and I'll respond as quickly as possible. On screen, you should see a link to my last video alongside a playlist that contains every single individual linear algebra guide video that I made so far. And I hope to see you in the next video. Until then, goodbye!